who's currently a postdoctoral fellow in mathematics at the University of KwaZulu-Natal and a PhD graduate of New Mexico State University in the US. Her seminar today is going to center on the Hofmann-Mislove theorem, which provides a fundamental link between topology and domain theory, and how it can sober McKinsey-Tarski algebras. Now, as a linguistics researcher, this was my favorite use of the word sober ever. So thank you very, very much for that. I really enjoyed it. And her research also addresses point-free topology and duality theory. So please join me in welcoming today's speaker. And over to you. Thank you, Ranjitha.
So first, let me introduce all the characters I've been using in my title. Hofmann and Mislove. They actually showed the two different objects. They have one from topological side and one from the algebraic side, and they were able to build a one-to-one correspondence between those two objects, given the spaces are sober. In a while, I'll explain what all these objects are and what sober spaces mean. But this is the whole picturization of Hofmann-Mislove theorem. And then what McKinsey-Tarski did was the power set algebras were generalized to a Boolean algebra with interior operators. That is, in a simple terms, the topological spaces were completely algebraic. So you can actually think of topological spaces in algebraic terms. That's what McKinsey-Tarski did. So we were going to work with complete Boolean algebras, and we call that something called as empty algebras. And that's the role of McKinsey and Tarski in this talk. And what I mean by when I say that they stay sober, so the Hofmann-Mislove theorem for the topological spaces needs the sober condition, and the Hofmann-Mislove theorem for the empty algebra setting also needs the sober condition. In between, I'll try to justify why the sober condition makes sense in both the cases. Okay. So moving on, let me just try to define all the terms one by one, Hofmann and Mislove. So Hofmann-Mislove is a very well-known result which connects duality theory, domain theory, lattice theory. So it's in a way giving a bridge between topology and lattice theory. So what are the two objects I mentioned in my first slide? What are the main two objects which we are concerned today? One, compact saturated subsets of X. So you have a topological space. I think compactness is something we're all very familiar with. Saturated, for me, it's just intersection of opens. So intersection of open sets, we are going to call it saturated. And the Scott-open filters, this is in the lattice of opens. As I mentioned, the Hofmann-Mislove theorem is giving us a picturization from a topological space to the algebra side. So the algebra side here we mean by the lattice of open sets. The lattice of open sets of a topological space, we call that something called as Scott-open filters. What is Scott-open filter? A filter is Scott in open sets, the collection of open sets is Scott-open. If I take the union of S in F, it implies there exists a finite subset of S such that union of T is within that filter. So if something satisfies this, it's Scott-open filter. And when we are in a sober space condition, there is an isomorphism between Scott-open filters, which was taken in the lattice of open sets, and compact saturated subsets, which was taken in the topological space. So now let's see this theorem in a more mathematical way by defining what actually this sober space is. We have been talking about sober for a while now, so we need to see what actually this sober space is. A closed set is joint irreducible if we cannot write it as the union of its proper subsets. What I mean by that, if F is equal to G union H, F should be either G or F should be either H. So that's joint irreducible. And what actually is sober, if every joint irreducible closed set, there is a unique point, which is a closure of it. So every joint irreducible, you can think of closure of a singleton set. That's how it looks like. Every joint closure. So usually closure of a singleton is always joint irreducible. When it is sober, every closed irreducible looks like that. So that's what sober means. What are the other equivalent definitions for sober? The other one is meet irreducible open. It simply means that same thing with closed set, we can just dualize it. the dual of closed will be the negation is open. So join irreducible will be meet irreducible. So every meet irreducible open, we can write it as a interior of a complement of a singleton, just like closure of a singleton. Now it's the interior of the complement of the singleton for a unique X. And the another way of looking at the sober spaces is every completely prime filter is of the form n of x, where n of x is just all the collection of open sets where x belongs to U. So these are completely prime filters. If all the completely prime filters look something like this, that's gonna be sober space. So this is all about the sober space. And then let me define Hofmann-Mislove in a more mathematical theorem setting. So I'm gonna set my all set of compact saturated subsets as K-sat. I will be using K-sat for throughout this talk. So K-sat will be compact saturated with the reverse inclusion. And S-filled will be Scott open filters. So collection of Scott open filters, I'm going to be using as S-filled. And the Hofmann-Mislove theorem says, for a sober space X, the compact saturated are isomorphic to Scott open filters. So this is more like a theorem setting, but I will be using the same K-sat and the S-filled throughout the other slides too. So this is the topological viewpoint. So Hofmann-Mislove has to give us a connection between some objects in topological spaces and algebraic objects. So what if we come from the other way around? What if we have to define Hofmann-Mislove from the algebraic point of view? So we can do that too. That's what frame theory comes in. So now we are going to see the same Hofmann-Mislove theorem from the algebraic point of view. So what are frames? Frames are complete lattice. When I say complete lattice, it's a poset where there exists supremum and infimum for all the subsets you take. And that's complete lattice. And it also satisfies infinite joint distributive law. That is, the meet for me is infimum, and the big V is the supremum. So that big V will be arbitrary supremum, and then the small wedge will be more like a binary one. So A meet join S is join of A meet S for every S in S. So A is coming from a lattice and S is a subset of a lattice, the frame, complete lattice. And that's the objects part. And what are frame homomorphism? Frame homomorphisms are which preserves finite meets and arbitrary joins. So we are going to call the category of frames and frame homomorphism by FRM. So category theory is a very beautiful language which lets us travel from one world to another world. If I have to go from a topological world to a frame world or frame world to a topological world, it's a very beautiful language. So I'm going to be using very little of that. So usually frame category will have objects and arrows. So the frame homomorphisms are the arrows and the objects are just the frames. So what is the best example we have already seen is if I have a topological space X, and if I take the open lattices, that's exactly a frame. So we can see that open lattice of topological, open sets of a topological space satisfies the condition which I mentioned in the definition. So that's the frame. And a frame is called spatial if it is coming from a space. So that's all it is. So if a frame comes from a space, it's spatial, as the name suggests. So what about the morphisms part? Now, if I have a continuous map in topological spaces between two topological spaces, I take the inverse image on the opens, and that's exactly my frame homomorphisms. So in a way, now I start from a topological space and I have a full route to go to the frame world just by taking the open sets and the inverse image on the open sets. So that's how we go to the from a topological space to frames. Now, how can I go from frames to topological space? So let's see that. For that, we need to define something called as a point. It's like just a meet irreducible. So as I mentioned previously, we did have that closed irreducible. The dual of that was meet irreducible. So I take the meet irreducible as my points. And I take all the collection of the meet irreducibles and I'm going to topologize it. I'm going to define opens on it. It's just all the sets of the form where A is a point in that is A is a meet irreducible such that U is not below A for all U in L. So I'm going to collect these kind of sets and make it a topology on the set of meet irreducibles. So now if we have a frame, we take the meet irreducible and it's always sober. So because remember sober condition was every meet irreducible has to be like that. Here, everything is meet irreducible. So of course this points of L is sober. So how about the morphisms? If we have frame homomorphism, we can definitely get the continuous map by just taking the adjoint and then restricting it to the meter reducibles. So we have a nice way to go from frame homomorphisms to continuous map. So this gives me a platform to go from frame world to the topological world. So I hope I have convinced like how to go back and forth now. So this is exactly what point free topology does. It's studying topological spaces without having to directly reference into points, because now we are in a way working with open sets. We are not working with the points. So we are working with the lattices structure, not exactly with the points of a topological space. So this is the, in a way, point free topology does. The primitive notion is open sets rather than the points itself. You can think of it something like that. So this is exactly the very famous theorem in point free topology. We always refer to Dowker-Papert theorem. The omega and PT, the one I described in the previous slides, gives a dual adjunction between topological spaces and frames to how to go back and forth. But when do they actually agree upon is exactly when they are sober and spatial frames. So there is an equivalence between sober spaces and spatial frames. So the frames are serving as the algebraic counterpart of sober spaces. So now we can now think, can we prove Hofmann-Mislove theorem in the frame setting? But we don't have to say it is sober. It's not required because sober and frames are one and the same for me right now, because we have established that sober spaces and spatial frames are equivalent. So now when I go to define the Hofmann-Mislove theorem, it doesn't make sense to have sober condition on it. So that's exactly what Hofmann-Mislove for frames are. For a frame L, compact saturated of points of L, just to remind, points of L is just meter irreducibles, is isomorphic to Scott-open filters of a frame. So it's exactly the Scott-open filters how we defined on the open sets, which is now Scott-open filters of L. This is Hofmann-Mislove for frames. So this Hofmann-Mislove doesn't just give us for spatial frames, but it gives for all frames. So of course, we can generalize a Hofmann-Mislove for sober spaces by this condition. How do I do that? Suppose I have a sober space X. This X is isomorphic to the points of opens of X, because remember points of L was sober, and we said that when it is spatial, they are both the same thing. So X is isomorphic to points of opens of X. And then now when I apply the Hofmann-Mislove for frames theory, I get the condition here. I don't know. Okay. So the condition here, K set of X will be isomorphic to K set of points of opens of X, because X was isomorphic to points of opens of X. And then that is isomorphic to Scott open filters of opens of X by the Hofmann-Mislove theorem for frames. Okay. So now we can think of this as a generalization of Hofmann-Mislove for sober spaces. So yes, now we did, the frame theory did give us a point-free version of Hofmann-Mislove theorem, because we didn't have to mention about points or anything. But still, somewhere we are referring points of a frame. So in the condition, we do have K set of points of a frame. Maybe it's not the point from the topological space, but it's points of a frame. So the question is, can we completely avoid points? It is difficult, right? Because we are trying to connect between topological spaces and algebra. So of course we have to talk about the points. So it makes sense for points of a frame to be existence in the Hofmann-Mislove theorem. But can we try to mention Hofmann-Mislove theorem completely not using the points? Can we do that? For this, we will see the answer very quickly, but this is a question. So that's where McKinsey-Tarski comes into play, the McKinsey-Tarski algebras. Let's see. So we generalize the lattice of open sets to get the frames, right? Instead of working with lattice of opens, what if we think, okay, what if I collect all the sets, not just opens, all the sets, the power set algebra with an interior operator, will it generalize a topological space? That's exactly what McKinsey and Tarski, based on the Kuratowski's axioms they built, they generalized power set algebra to Boolean algebra with an interior operator. But what we work with, what we call it empty algebra, is a complete Boolean algebra with an interior operator. And it satisfies the interior operator axioms like how we would expect the interior operator in a topological spaces would do. The box one is one. The interior operator, I'm going to refer it by box. Box A is below A. Box of A meet B is box A meet box B. And box A is below box A. These are the properties of the interior operator. So what is the motivation for the morphisms on the empty algebra now? So we remember that in the frames, we had a continuous map. We took the inverse image on the opens, we got a frame homomorphism. Very similarly, if we have a continuous map between topological spaces, we take the inverse image on the power set algebra. It satisfies this particular axiom, F inverse of interior of A is below interior of F inverse of A. And I think we would have seen in our topology courses, when continuous map is open, we actually get this is equal to. There is an equal to instead of the subset thing. But we are more concerned with working with topological spaces with continuous maps. So as a result, we are going to just generalize this to the empty morphisms, which is just a complete Boolean homomorphism with h of box A is below h of box of h of A. Just to the generalization how we can see from the topological side. So, and we are going to call the category empty, where it consists of empty algebras and empty morphisms. So now that we have this, how to connect this with the empty with the topological spaces and empty with the frames, which we already defined. So let's see how to go from an empty algebra to frame. So suppose I have an empty algebra M, and A is box A, that is, it's fixed under this interior operator. We call it open, right? That's no surprise because in the topological spaces, every open is interior of itself. So those we are going to call it open. And it's closed if the negation is open, or you can say negation A is closed. If A is open, negation A is closed. And you can also think of it as a fixed under diamond A, like a closure. So this diamond is just a closure, how we see in the topological spaces. So we are going to collect the collection of open elements, and that's our O of M. O of M will be the collection of open elements. This O of M is not just a collection of open elements, it also gives us a functor from empty to frames. It gives us a transportation to go from an empty algebra world to the frame world. And this is also an essentially surjective functor. What do I mean by essentially surjective functor? It's very similar to how surjective works on functions, but I'm not going to get into the detail, but that's what happens there. So this is how we go from empty to frame. How about empty and top? So as we already, that was the whole motivation, right? If I have a topological space, I take a power set algebra that gives me my empty algebra. And the empty algebra which comes from spaces are atomic. So it's called spatial. Exactly. That's how the name suggests. So if an empty algebra comes from a space, it's just spatial. And conversely, how do I go back? Suppose I have an empty algebra. How do I go to the topological spaces? I take an empty algebra M, and we take all the atoms of M, and then we topologize it by giving the open such that the set of all atoms below an open element. So that will be the open sets for the set of atoms of M. And this is the category of spatial empty algebras. Once it's atomic, we just add S layer so that we say spatial empty algebras, SNT. So now we get this beautiful adjunction to go from topological spaces to empty algebras, and empty algebras to topological spaces, this power set and atoms. But when do they become an equivalent? That is exactly when they are spatial. So topological spaces and spatial empty algebras are equivalent. So now let's just compare the both things. So now we saw Hofmann-Mislove for pseudo-spaces, and we have seen Hofmann-Mislove for frames. And now I have to convince everybody that why sober is required in McKinsey Tarski too, right? So this is what is happening here. So sober spaces are capturing, spatial frames are capturing, or frames are capturing all the sober spaces, but empty algebra is capturing all the topological spaces. So we can actually define what sober means in the empty algebra because it's able to capture anything below or before sober also. So that's what's happening here. So empty algebras capture all topological spaces, and then this makes more sense that you have to add soberness into the empty algebra condition if I have to do the Hofmann-Mislove theorem in the empty algebra setting. So yeah, let's move on to see what Hofmann and Mislove theorem in empty algebra looks like. So if I have already convinced everybody this empty algebra has generalized topological spaces completely, that means we can capture all topological spaces. It should not be hard for us to see how the compact saturated or anything we see in topology, how to get it in the empty algebra language. So it's very simple. So what is compact? Just like how we would expect, element A is compact if for each collection of opens such that A is below join of S, it follows that A is below a finite join of finite subset of S. So this is very similar to what we see in our topological spaces, right? So it's the same thing. Not the same thing, it's very clear to see. So now exactly like that, saturated was just intersection of opens. Here it would be meet of opens. So that's saturated. And sober also, we can define sober here. An empty algebra is sober if each closed join irreducible, there is an atom such that C is equal to diamond X. If we remember any of this kind, like in the beginning of the slides, this is exactly what my sober condition for topological spaces was actually. So we just start generalizing everything that happens in topological spaces to empty algebras very quickly. So now we have what is compact, what is saturated, what is sober. So we have collected all the ingredients required for Hofmann-Mislove. The one thing missing is Scott-Open filter. So let's see that. But that Scott open filter was actually defined in lattice of open sets that came from an algebra side, right? It did not actually come from topological side. So now here we cannot directly generalize what Scott open filter was in the empty algebra language. We can generalize, but we have to be a little bit careful because it was defined in the open sets, lattice of open sets. So if I have a topological space X, there is an embedding of filters or filters of open sets into the filters of a power set. So you have to just take an upset. Let's say this is this is lattice of open sets. This is a power set. Then all you have to do is take a filter in the lattice of open sets and you take the upsets, and then you get a filter in the power set. But these kind of filters satisfy an extra condition that for every element A in that filter, the interior of A also will be in the filter. So this is the one small thing we need to add in the definition of empty algebras, Scott open filters when we do it. So that's exactly what I'm going to do. So an empty algebra, we call something an open filter if A in F implies box A in F. So that's the condition. And then Scott open filter is very similar to how we had in the open set. Open filter F of M is Scott open if for each directed family S in O of M from join S is equal to in F follows S intersection F is non-empty. This is a very similar what I had before. Join of S is in F. There exists a finite subset. It's the same thing, but I have just written it in a different way. This is Scott-Open filters in empty algebra. So I think now I have everything I want. Scott-Open filter, compact, saturated, and sober. So I'm ready to define. So if we have a sober empty algebra, the Scott-Open filters of M is isomorphic to compact saturated elements of M. So this is the main theorem for empty algebras. Now I want to see that we get the Hofmann-Mislove for frames using this. So let's start from a frame. The Scott-Open filters of a frame are isomorphic with Scott-Open filters of opens of points of L. And that's something we have to prove a little bit. And then after that, the third one comes from the fact that where I said you can find a correspondence between open filters of opens and filters of power set. So that's the second one. And the last one is where I'm using my Hofmann-Mislove for empty algebras. Scott open filters of power set of points of L is isomorphic to compact saturated of points of L. So in this sense, the Hofmann-Mislove theorem for empty algebras generalize it for frames, but we already saw the one for frames will generalize for sober spaces. So in a way, we are able to capture both of them with empty algebra setting. But the question we raised in the beginning was, can we actually formulate it without referring to points at all? So we talk about point free, right? So can we do this completely without the points? Of course, yes. The theorem there in the empty algebra setting, there is nowhere I have defined the points. So the points for empty algebra was actually atoms, right? There is nowhere that we haven't used atoms at all when we define this Hofmann-Mislove for empty algebras. So now we can easily say it's completely point free. The Scott open filters of an empty algebra is isomorphic to compact saturated elements of an empty algebra. So we were able to manage to get this whole thing point free now. And then this, as we said, this is a very nice result. Hofmann-Mislove theorem is a very nice result. So as a consequence, we also get many nice results for empty algebras too. So using the Hofmann-Mislove, we will be able to derive some nice point-free topology dualities like Hoffmann-Lawson, Ispel, and Stone dualities. So again, these ones, as I move forward, you will see like how easily we can generalize some of the things we see in topological spaces to empty algebra setting. Let's start off with what is locally compact empty algebras. So in the topological space, a space is locally compact for each open set U and an element X in U. There exists an open set and a compact set such that X is in V, V is in K, K is in U. So we get this pair, V and K. So, and what happens on the morphisms level is if you have a continuous map, we call it proper if F inverse of a compact is compact saturated. So that's something what we call proper. So we can just generalize it to the empty algebra setting. So we say A is related to B. I haven't given any name for this. For now, I'll just call triangle. A is triangle B if there exists a compact element in between them. That's exactly what was happening in the topological spaces. And then we say it's locally compact if every open can be generated. What I mean by generated is every open can be written as opens, which is in this triangle relation with U. U is join of V such that V is in triangle with U for all the opens. And the empty morphism is simply the compact saturated goes to compact saturated. That's proper. And this is locally compact empty algebras. And then what do we have on the frame side, which is equivalent to locally compact, is continuous. What does continuous mean? So again, here we have a name for it. We call something way below, that is A is way below B, provided whenever B is below join of S, there exists a finite subset of S such that A is below join of B. So then we say A is way below B. And if every element is generated by way below elements of that, it's continuous. That is A is join of B, where B is way below A, then it's called continuous. And the frame homomorphism is proper if this is preserved. So now locally compact sober empty algebras and proper empty morphisms will be LC sob empty, and then continuous frames and continuous frame homomorphisms. And LC sob is locally compact sober spaces and proper continuous maps. So in this, if someone has seen already point-free topology, in point-free topology or in the frame theory, once you have continuous frames, it's always spatial. But here, for locally compact sober, we unfortunately don't get that. Not unfortunately, it's a different topic, yeah. So we have to add that SMT here. We have to make it spatial here. So once we do that, we get an adjunction between locally compact sober empty algebras and continuous frames, and then we get an equivalence once we go to the spatial part. So from this, we can actually derive that locally compact sober SMT is equivalent to LC sob. So this is exactly what Hofmann loss and duality is. This is a very well-known duality in one of the well-known dualities. So continuous frames is dually equivalent to LC solve. Just by combining those two dualities, I can get the Hofmann loss and duality as a corollary from the empty algebra setting one. So this is what is happening. This is the picture of locally compact sober spaces, locally compact sober empty algebras, and the continuous frames. Okay. The next we have compact house of empty algebras and regular frames. So compact, I think we already saw what compact is. What Hausdorff condition is. Hausdorff condition, again, these are all point free now. So Hausdorff is if every element A can be written as join of elements AIs, that each AI will look like meet of diamond box C. So this is the Hausdorff condition for empty algebra setting. And M is compact if just the top element is compact. Top element is just one. If that's compact, the empty algebra is compact. So in the frame setting, what we have is regular, because Hausdorff condition is very difficult to define in the point in frame setting. So we don't do Hausdorff, but we have regular there. So what is well inside? We say A is well inside B, provided that A star is join of B. The A star is just a pseudo complement. And we say it's regular if every element A is join of B, such that B is well inside A for each A in L. So this is the analog we have for Hausdorff regular part. Okay, so now we have compact house of empty algebras, K house empty, and then K regular frames and K Hausdorff. So once we have that, we have an equivalence between compact Hausdorff to compact regular. So the thing here is before I had to add the special part to it, but here once you have compact Hausdorff, empty algebra is already special. So here I don't need to add that extra special condition. And then there is a dual equivalence between compact house of empty and compact Hausdorff. So as a result, as a corollary from these two, what we get for the empty algebra setting, we can get a corollary as that's Isbell duality, that compact regular frames are dually equivalent to compact Hausdorff spaces. So this is the Isbell duality. And then this is the whole picture of compact Hausdorff empty algebras, compact Hausdorff spaces, and compact regular frames. So next is zero-dimensional empty algebras. So this, I'm going to define what stone spaces are equivalent to, like stone empty algebras. That's why I'm going to define what zero-dimensional are. But for that, I need T1 algebras. T1 algebras are where every element is join of closed for each A in M. If we actually recall, every set is just like every singleton is closed in T1, right? Every singleton is closed. And singletons is what creates the whole subset, whole set. Like if I have a set A is just union of singletons, where singletons are coming from A, and all the singletons are closed. So if you think about it, it's exactly what it's doing here. A is join of closed for each A in M. That's what the T1 algebras are. And then element is clopen if it is both open and closed. And it's zero-dimensional, one if it is T1 algebra, and if every open can be written as join of clopens. So, and something is stone empty algebra if it is zero-dimensional, compact, and Hausdorff, all three. So that's on the empty algebra side. Now I'm going to define on the frame side. So we say C is complemented if C joins C star is 1, where C star is the pseudo complement. Pseudo complement simply means join of all the elements such that C meet X is 0. And we collect all the collection of these complements. See, again, we can't talk about closed and open in the frame setting. So that's why we have this complemented and pseudo complement versions. So L is zero-dimensional if for every A in L is join of complemented elements below it. It's stone if it is compact and zero-dimensional. So if we have stone empties, stone empty algebras, stone frame is compact regular frames with stone zero-dimensional, and stone, which is just stone spaces, then we get the dual equivalence between compact Hausdorff empty algebras and compact Hausdorff spaces, and stone empty algebras and stone spaces. And the same thing with compact Hausdorff and compact regular, and stone empty and stone frame. So as a corollary, we get the stone duality, which is stone frame is dual equivalent to stone. So the stone duality, the one famous one is actually Boolean algebras to stone spaces. We can do that too, but here what I mean by stone duality is between the frames part and the stone spaces part, not the Boolean algebra one. So this is the whole picture: stone spaces, stone empty algebras, and stone frames. So all the consequences, whatever I defined so far, we could have easily gotten the same thing for local compactness by replacing the compactness. So local compact Hausdorff are dually equivalent to continuous regular frames, and locally stone empty algebras are equivalent to locally stone spaces and hence locally stone frames. So the compactness could have been replaced with locally stone, and everywhere it would follow locally stone. So, and this naturally describes the duality for locally stone too. So it can be done locally too. And this is the whole picture of what I did so far. And thank you.
Thank you, Ranjit. I will open up the chat for anyone who's online that would like to ask any questions.
Hi, thanks very much for the nice talk.
Thank you.
Could you just go to slide 26? I'm really interested in these MT algebras. Yeah, so there, did I, sorry, yeah, just back.
This one?
26.
I can't see my slide number, so just give me a second.
Okay.
Yeah.
Did I miss the definition of Hausdorff for an MT algebra?
Yeah, I can go back.
Was it earlier?
This one? This is the one definition.
Okay, okay. So you.
So every singleton in an Hausdorff is actually intersection of closure of opens containing that point.
Okay, okay.
So I've
and
just
then
generalized that.
I see. Okay, so is this part of your work? This wasn't.
Yeah. This is what empty
okay.
algebras is my work.
Okay, so I see, and then maybe it's slide 29. Yeah, so I'm interested here because there's this dual equivalence between stone empty algebras and stone spaces, right?
Oh, stone empty algebras and stone spaces. Yes, correct.
Okay. And so now there's a one-to-one correspondence between stone spaces and all Boolean algebras.
Yes,
right?
yes.
But now a stone empty algebra it's got to be a complete Boolean algebra, and it's got to have an interior operator and then satisfy some additional conditions.
Correct.
So there's a one-to-one correspondence between stone spaces and all Boolean algebras, but now we're restricting to complete Boolean algebras.
Yes.
But does it mean then that on any complete Boolean algebra, there's going to be more than one possible interior operator?
Yeah. Yes, we can do that. Yes, like the interior operator doesn't have to be unique. So you take a complete
Okay,
Boolean
okay.
algebra and we can define a. So and if you're thinking of, okay, we have Boolean algebras and stone spaces, right? We can because now stone spaces and stone empty algebra are in equivalence. We can also do this equivalence from Boolean algebra to stone empty algebra. We can go back and forth.
Right. Okay.
Yes,
Okay. So you kind of shrink the number of possible underlying Boolean algebras by requiring that they're complete, but then
Yes.
you expand the class again by the different interior operators. That,
Yes. Yes.
okay,
Yes.
okay,
Correct.
okay.
Yeah,
Now that makes
yes.
sense. Yeah, good.
Yes.
Okay,
Yes.
nice.
Yes.
Okay, yeah, thanks. That's I see there's something in the chat as well. I don't know.
That's true. That's true. But what I mean by we are not using points is we are not taking any functor. That's what I mean. I know we are hiding the point that there are atoms, but there are not many, right? There are atoms like it. So this is true even if you take a complete atomless Boolean algebra. No, but no, the soberness will be like, and you can still have something very trivial and you can still do it, right? So that's, and what I mean is we are not using points as the main thing in the theorem, if that makes sense. Okay, thank you.
Otherwise, thank you very much. We will now end the meeting. Thank you everyone who attended. Enjoy the rest of your day.